All right, you guys, so I think I got cut off at the very end of that last video where I was showing you a slightly simpler way to do it with your calculator. So just so you know, in order to do this operation, which is a choose operation, that means of 4 operations, you're choosing exactly 3. You can find that in your calculator by picking 4, and then the operation that you want to select, you get by going to Math, and then once again, we're going to Probability. But this time you want to pick the option that's usually the third one down of NCR. That means of the number, you pick 3 of the given results. So enter that into your calculator after you've already entered a 4, and then do 3, and you'll get that option of 4, which is what we found with this factorial operation. So multiplying by the same P and Q exponential expressions here will get you to that 0.0256 probability one more time, but it's going to do so in a much more efficient way. Now we want to be able to answer a couple of different questions when it comes to binomial probability distributions, because we can be asked about very specific events, or we can be asked about some events in combination with one another. So all of the work that we just did answered the question of the probability of hitting exactly 3 balloons. So that was probability of 3 successes, which we found to be 0.0256. But let's then answer this question so we get a little bit more practice. What's the probability of hitting exactly 4? Well, we just need to use this formula again. But remember, this formula can actually go by pretty fast in our calculator because we are taking 4 and we're interested in 4 successes. So the first thing we can put into our calculator is 4, and then we can pick 4. So we want to perform this operation. So go ahead and plug that into your calculator. choose 4. And when you do that, you just get 1. Then you're going to multiply by probability of success, so 0.2. raised to the number of successes, which is your x value, so 4 in this case. And then q is your probability of failure, so 0.8. Here, n minus x is going to be 4 minus 4, because 4 darts, 4 successes, so this is going to be to the 0 power. So this will end up being 1 times 0.2 to the 4th power, and then anything to the 0 power is just going to be 1. So your final probability value is going to be 0.016. Now notice that's the same as if we'd done some of our basic discrete probability work. Probability of all successes is just multiplying the successes by itself 4 times. So probability of hitting all 4 is 0.0016. So we've answered that one successfully. Now the last one that we have to answer is the probability of hitting fewer than 3. So there are 2 different ways to answer this question. One of the ways I can answer the different probabilities of hitting fewer than 3 balloons is that I could find the probability of hitting 0 balloons, and then add that to the probability of hitting just 1 balloon, and then add that to the probability of hitting 2 balloons. And I could add those values up and see what I get. That wouldn't be too hard, but it would involve 3 more additional binomial calculations beyond what we've already done. The good news is, though, is that we know if we were to add probability of 3 here and probability of 4, all of the different probabilities together have to equal 1. So if we're interested in these probabilities, so the ones that are smaller than 3, well, we can just subtract these 2 values from 1. And we've already calculated those 2 values here and here. So I can answer the question of what's the probability of hitting fewer than 3 balloons by taking 1 and subtracting off 0.0256, the probability of hitting 3, and 0.0016, the probability of hitting all of the balloons. So when I do that, 1 minus 0.0256 and 0.0016, the final answer that I get is 0.9728. So if you're a carnival game operator, that's good news because you have a 97% chance that people are going to be hitting fewer than 3 balloons when they go to play this game. So that's our first example of binomial distribution work and the associated probabilities. We want to try one more probability so we feel confident approaching any different scenario, both in recognizing that it's binomial and then in using our calculator to get to the answer pretty quickly. So our second example deals with Christmas tree lights. This one says, consider that you're putting up Christmas lights in a strand around your staircase banister. There are 20 lights on the strand. Each of the lights individually, has an 88% chance of remaining fully lit throughout the holiday season. What is the probability exactly 18 lights will remain lit throughout this time? So, checking our binomial distribution conditions really quickly. Here we have a binary event. The success is defined as the light staying lit, and then the failure is going to be the light burning out, or the battery failing, whatever it is that causes the Christmas light to not light up. So it meets that condition. Then it's independent. So all of the lights are independent of one another. The fact that one goes out isn't affecting the other, although that was true with old Christmas tree lights. So we're good to go there. Then we need to know that P and Q stay the same. So P is the probability of success. In this case, that's 0.88. Probability of failure then is 0.12. And those values are going to stay the same. It's not like they're going to change light by light. Last up, we want to know, do we have a fixed number of trials? So here, the trials are our number of lights. So because we have 20 lights, that's a fixed number. We're not varying the number of lights on the strand as we're performing this operation. So once we know it meets the binomial conditions, we can ask ourselves about this second step. How can we manually identify the sample space of this situation and the associated probability outcomes? Well, the short answer is we can't manually do this because that would be painful and we could spend close to our entire lives doing that. Because if there are 20 lights and you have two options of success and failure, you guys, that means your sample space is going to be 2 to the 20th power. So if we plug that into our calculator, 2 to the 20th power, we get out this big old number. So that is 1,048,576 different possible outcomes of successes and failures amongst our 20 lights. So we do not have time for that. We're going to go straight into doing that with our calculator instead. So with our calculator, we can answer the specific question that's posed in this problem, which is, what is the probability that exactly 18 lights, excuse me guys, will remain lit? So if we want to define our values here, n is 20, that's the number of trials. The probability of successes that we're interested in is equal to 18. Our probability of success, like we talked about before, is 0.88. Probability of failure is 0.12. So if we go to use this formula here, again, we want to use that choose option in our probability because it's going to go by faster. So probability of 18. We first start out by calculating this piece here, which we do so by inputting 20, and then of those we're choosing 18. So get that value out of your calculator first before you go to do the exponential probability piece. So 20, hit your math button, tab to your probability, select option 3, and then pick 18. So that should give you a value of 190. Then you're going to multiply that by your p-value of 0.88, raised to your x value, which is 18. Then you multiply that by your q value, which is 0.12. And then here, our n minus x, that's the number of trials minus number of successes. So number of trials is 20, number of successes is 18. So 20 minus 18 is going to be 2. So this is going to be raised to the second power. So let's go ahead and multiply that whole thing out. 190 times 0.88 raised to the 18th power times 0.12 raised to the second power. So if you do that, the value that you should get out is 0.2740. So So we've got a 27% chance that exactly 18 lights are going to remain lit throughout the holiday season, so 0.2740. So that's our third step, but we do have a couple more different types of questions that can be posed that are pretty easy to get through mathematically. So let's wrap up these examples by taking a look at the fourth step option. So the fourth step asks us, what other kinds of questions can we check out? So the question we just answered was the probability of exactly 18 lights remaining lit. So probability of x being 18, we found was 0.2740. So let's take a look at what else it asks us. What's the probability of more than 18 lights being lit? So if we want to know more than 18, that means the probability of x being bigger than 18 is going to be the probability of 18 plus the probability of 19 plus the probability of 20. So each of those three options. So we've got 18, which means we need to calculate probability of 19 and 20. So let's see how fast we can do those. Probability of 19, that means I'm going to input into my calculator 20, pick 19. When I do that, so 20, math, probability, pick 19, I get out 20. Then I multiply by my probability of success raised to my x value, which is 19, times my failure, 0.12 raised to n minus x, so 20 minus 19 is 1. When I put that together, 20 times 0.88 to the 19th power times 0.12 to the first power, I'm getting out a value of 0.2115. Then I can calculate the probability of all 20 staying lit. So first up, I want to do the 20, pick 20. And when I do that, anytime that you have the total number that you're selecting, that value is always going to be 1. Then I multiply by 0.88 to the 20th power times 0.12. Here, n minus x, if I have 20 trials and 20 successes, is going to be 0. So this is just going to end up being 0.88 to the 20th power. That's all I actually have to plug into my calculator. So that's going to be 0.0776. So I just need to add my three probabilities together. So this will be 0.2740 plus this one, 0.2115, plus this one, 0.07, oops, it's a funky 76. So go ahead and enter those values into your calculator, 0.2740 plus 0.2115 plus 0.0776, and you should get out 0.5631. So we have about a 56% chance of 18 or more lights staying lit. So that means the last question we can answer pretty easily is the probability of fewer than 18 lights staying on. So this then just becomes a complement probability because I've already identified the probability of more than 18. And so since my probabilities up to 20 have to add to 1, I can just subtract this guy right here. So 1 minus 0.5631, if we evaluate that in our calculators, is going to be 0.4369, or about a 44% chance that fewer than 18 are going to stay lit. So that's it for our probability calculation work today, you guys. Please go ahead and retry the Khan Academy practice if you haven't had a chance to do so yet, or you have the rest of class time to work on your textbook homework from your stats textbook. If you need to run into my classroom, please just ask Miss M if she can open up the door for you so you can go and get one from the drawers. Otherwise, you guys have a wonderful weekend. I will see you on Monday. And also, happy PA today, you guys. Bye.